Okay, so time for section 4 of chapter 6 called the Fundamental Theorem of Calculus. So in this lesson, we're going to evaluate a definite integral using what's called the Fundamental Theorem of Calculus. And don't worry, we'll explain what that is. Understand and use the mean value theorem for integrals. Find the average value of a function over a closed interval. Understand and use what's called the second fundamental theorem of calculus, and understand and use the net change theorem. So a lot of information in this section. I'm going to break it up into a couple videos here for you. So let's first talk about fundamental theorem of calculus. So far you've been introduced to the two main branches of calculus. One's called differential calculus, and that got started kind of from the tangent line problem. And now integral calculus, which kind of started with the area problem. So at this point, these two problems might seem unrelated, but they actually have a very close connection. The connection was discovered independently by Isaac Newton and Leibniz, and is stated in a theorem that is appropriately called the fundamental theorem of calculus, because it shows how fundamentally differentiation and integration are related. Informally, this theorem states that differentiation and definite integration are inverse operations, in the same sense that division and multiplication are inverse operations. In other words, they kind of undo one another. To see how Newton and Leibniz might have anticipated this relationship, look at these approximations below. So when we did the tangent line problem, we took the slope of the secant line through a curve, 2 points through a curve, and took the limit as the one point approached the other one to get the tangent line. So the slope is approximately the change in y divided by change in x. The area of a rectangle, the area under the curve, we first approximated with a rectangle. So we had the change in y, which would have been the height, times the change in x, which would have been the width. And then we took the limit as the thickness of the rectangle approached 0. So the area was approximately base times height, which is change in y times change in x. So they have this kind of inverse relationship there. The slope of the tangent line was defined using the quotient, change in y over change in x, and the area of the region under the curve was defined using products of the change in y times the change of x. So at least in the approximation stage, the operations of differentiation and integration appear to have an inverse relationship similar to that of multiplication and division. So the fundamental theorem of calculus states that the limit process used to define the derivative and definite integral preserve that relationship. So the fundamental theorem of calculus looks like this. If a function f is continuous on a closed interval a to b, and f is an antiderivative of little f on the interval a to b, then the definite integral of little f is equal to capital F of b minus capital F of a. In other words, capital F stands for the antiderivative of little f. So when you integrate, you take the antiderivative, plug in the upper limit, the lower limit to the antiderivatives, and subtract. How awesome is that? So here's the guidelines that can help you understand and use the fundamental theorem of calculus. So first, provided you can find an antiderivative of f, you now have a way to evaluate a definite integral without having to use that long limit of a sum or using the long Riemann sum definition. When applying the fundamental theorem of calculus, this notation is what we're going to use right here. So the definite integral of f of x dx equals capital F of x evaluated at b and a is what this means. And then you plug in b and plug in a to the antiderivative and subtract. For instance, to evaluate the integral from 1 to 3 of x cubed, you can write the integral of 1 to 3 of x cubed dx equals the antiderivative of x cubed is 1/4 x to the 4th, and the bracket with the 3 and the 1 indicates that you're going to plug in 3, plug in 1, and subtract. So we do that. 3 to the 4th over 4 minus 1 to the 4th over 4 gives you 81/4 minus 1/4, which is 80/4, which is 20. So it's not necessary to include the constant of integration c, because if you did, when you get to the evaluation part, the capital F of b minus capital F of a, the c's would just cancel off anyway, no matter what they are. So actually, whenever you're doing a definite integral, the plus c doesn't matter. If you have an indefinite integral, in other words, the limits aren't there, the 1 and 3 weren't there, you're just getting the antiderivative, you have to put the plus c. But When you're doing a definite integral, it's not necessary. All right, so let's check out an example. I want to evaluate each of these integrals. So part A, you just take the antiderivative of x squared, which is 1/3 x cubed, and minus 3, which would be negative 3x, bracket 2 and 1. So you plug in 2 to this whole function, so you would get 8 over 3 minus 6, and plug in 1 to the whole function, so you get 1 over 3 minus 3, and then subtract those two values. These parentheses are important because you want to subtract the value of f of 1, which is given by 1/3 minus 3. So you would get negative 2/3. B, the 3 times the square root, you could rewrite that, factor out a 3, and 1/2 exponent. So the new exponent would be 3/2, multiply or divide by 3/2, and you would get, or you can multiply by 2/3, I like to multiply by 2/3. Then the 3's would cancel and you just have 2 times x to the 3/2, so plug in 4 and 1 and subtract. You get 14. Now remember, 3/2 power. When you have a fractional exponent, the numerator is the power and the denominator is the root. So it's like you're going to cube it and take the square root, or you can take the square root and cube it. So the square root of 4 is 2, cubed is 8, times 2 would give you 16. And 1 to the 2/3 power is just, or 3/2 power rather, is just 1, because whether you root it or exponentiate 1, you still get 1. So times 2 gives you 2. So 16 minus 2 gives you 14. All right, so how about if we had an absolute value problem? We'll just get one of these black sheep out of the room, or the white, or the pink elephant in the room, whatever you want to call it, out of there. Talk about it. So using this picture and the absolute value, you can rewrite the integrand as shown. Now remember, for the absolute value, this part right here, the increasing part, is just the graph of y equals 2x minus 1. And this part is the graph of the opposite of 2x minus 1. So negative 2x plus 1 is how you could write that. So you have to split it up into its two parts and integrate the one function over the interval where you use that. So it looks like it would be from 0 to 1/2, and then do the other one from 1/2 to 2. Okay, so you can write the integral in two parts. So the integral of the absolute value is the integral from 0 to 1/2 of the negative 2x minus 1, plus the integral from 1/2 to 2 of the 2x minus 1. So if I distribute the negative, it would be negative 2x plus 1, anti-differentiate, you get negative x squared plus 1, plug in 1/2 and 0 and subtract those to evaluate this integral. The antiderivative here would be x squared minus x, plug in 2 and 1/2, subtract those, and this is what it would look like. So it's this one evaluated at 1/2 right here, and 0 right here, and subtract those. And then this represents this integral, so you evaluate it at 2 and 1/2 and subtract those. And when you simplify, you get 5/2. Now you can use this method to evaluate pretty much any absolute value of function that you're going to do, even if it's like absolute value of x squared minus 4, something like that. Okay, what you want to do is how they figured out how to get the 1/2 is you just take the function that's in the absolute value and set it equal to 0. So if you add 1 divided by 2, you get x1 equals 1/2, and that's the point where it kind of is the corner there. If it was absolute value of x squared minus 4, that graph is like the graph of x squared minus 4. So it's like a parabola shifted down 4 units. However, when you take the absolute value, it flips over the negative part. So this part wouldn't be there. And then you'd have these 2 points here. Well, all you'd have to do is set that equal to 0, add 4, take the square root, and you get x equals plus or minus 2. So the part that kind of got flipped over is the part that you have to take the opposite of. So if I was doing the integral from, let's say, negative 6 to 7, I'd have to break it up from negative 6 to 2, to negative 2 rather, then the integral from negative 2 to 2 of the opposite of x squared minus 4, because that's the part that flips it over, and then the integral from 2 to 7 of x squared minus 4. Hope that was helpful to you. All right, let's find the area of the region bounded by the graph of y equals 2x squared minus 3x plus 2. The x-axis and the vertical lines x equals 0 and 2. So if you graph all of those, here's the graph of the function, the x-axis, the vertical line x equals 0 and x equals 2. The shape that's trapped in there is the region. Okay, so we can set that up as a definite integral. So all you do is integrate the region over the interval. So you anti-differentiate, you'd have 2/3 x cubed minus 3x squared over 2, or 3/2 x squared, plus 2x. Again, you don't need the plus c. Then you would plug in 2 and 0 and subtract. So plugging in 2 gives this, and 0 gives that, subtract. And you get 10/3. So the area of this region is equal to 10/3. All right, guys, that's it for this section. Please continue on to the next video.